So in previous lecture we have finished with the Kohlrausch law of independent migration, and for the weak electrolyte as well as strong electrolyte, this law is applicable. Okay? Now what is that law? So that law is simply the total molar conductance of a given electrolyte at infinite dilution will be the what? Summation of its constituent conductance of ions. So again we have seen like one important relation, that is this degree of dissociation alpha can be correlated with the molar conductance at a particular concentration, that is say lambda m upon lambda naught, okay, at infinite dilution. So we can say this alpha is equals to degree of dissociation is equals to this molar conductance at infinite dilution to the molar conductance at particular concentration to the molar conductance at infinite dilution. Okay, so that is the one important again relation, and this is also a important statement, okay, mathematical form of the given statement for the Kohlrausch law. So lambda m naught is equals to lambda naught of cation plus lambda naught of anion. So experimentally we have already found out the various values for the given ions, like for H plus, K plus. So these are the easily obtainable value because they containing in the salt or strong acid as such. But what we will do for the acetic acid? So in order to find out the limiting molar conductance of weak electrolyte like acetic acid, we just simply need to add the H plus and acetate ion molar conductivities. So we will get the molar conductivities for the acetic acid at infinite dilution. So there are the quite important three applications of this Kohlrausch law. So first application is what? Determination of limiting molar conductance of a weak electrolyte. So in order to determine the limiting molar conductance of weak electrolyte, like we can measure the conductance of that particular salt, weak electrolyte, consider acetic acid. But does it dissociate completely? No, it does not dissociate. So in order to find out its molar conductivity, it has to be dissociated completely. So we cannot like directly find out the molar conductance for acetic acid. So we will use this Kohlrausch law in order to find out that. So how will you actually use this? So by extrapolation of that graph of lambda versus square root of c, we cannot find out the lambda m naught value. So based upon this Kohlrausch law, it is possible to calculate the limiting molar conductance of weak electrolyte by simply adding the and subtracting the lambda m naught values of various electrolyte. So consider the electrolyte like acetic acid. So if you want to find out the value for molar conductance of acetic acid, how can you obtain acetic acid? So acetic acid has the formula of CH3COOH. So if you have the certain constituent consisting acetate ion and certainly considering H plus ion, so we can add that ions. Okay, so this acetate ion can be obtained from the sodium acetate. So sodium acetate is taken here, plus for this H plus we can take the H plus ions from the HCl. So this is the HCl. Now we have been extra what? Here Na plus ions are extra and here Cl minus ions are extra. So we have to subtract that ion. So that is lambda m naught of NaCl. So likewise we can find out the molar conductance at infinite dilution. And if you have given the table, directly you can add the H plus ion and acetate ion conductivities at infinite dilution, and simply if you add it, you will get the molar conductivity at the infinite dilution for the weak electrolyte, that is acetic acid. Now for the weak electrolyte other than this univalent, because till now we have seen only the univalent ions, the molar conductivities which can be evaluated by the expression lambda m naught is equals to what? Q into lambda plus of infinity plus R into lambda minus of infinity, that is Q and R what? The stoichiometric coefficient that are in the given formula. Means suppose that we are having ammonium sulfate or sodium sulfate, likewise there are the differing in their stoichiometric coefficients or proportion. So we have to take into that also in the given account. Means number of ions will be increases accordingly the molecular formula of the given electrolyte. Okay, So now consider the one example based upon this Kohlrausch law. Now calculate the molar conductance of ammonium hydroxide at infinite dilution. The molar conductance at infinite dilution of ammonium chloride is ammonium chloride, ammonium hydroxide and NaCl are respectively, that is 0.04197, 0.02481 and 0.01265 cement centimeter meter square per mole. So what they are asking, ammonium hydroxide. For ammonium hydroxide, how can you obtain that? So for that we first need the ammonium ion which can be obtained from ammonium chloride, then hydroxide ion which will be obtained from sodium hydroxide. So what is the extra here? So extra is NaCl. So we need to subtract that NaCl molar conductivities. So if we done that, you will finally get the answer of around 0.02713 cement meter square per mole. So you can see this, the molar conductance for weak electrolyte is very low. Okay, now consider the second application, which is the dissociation constant of a weak electrolyte. So previously we have seen the what do you mean by dissociation constant and what do you mean by formation constant. Okay, so dissociation constant, which can also be simply said by the equilibrium constant, like here you can see this Ke, that is the equilibrium constant. So considering the dissociation of a weak electrolyte like Ba dissociated as B plus and A minus, so applying the law of mass action to the above equilibrium, we can get what? Concentration of product upon concentration of reactant, that is the equilibrium law, or this is also called as a dissociation constant of a weak electrolyte, which will varies what only with the temperature. Now we can correlate this dissociation constant with degree of dissociation, that is alpha, and degree of dissociation can be correlated with what? The molar conductance. So we can do that by using certain simplification, like consider first we need to convert this concentration into degree of dissociation. So the molecule will totally contain what? How many concentration is there? So that is C moles per dm cube of the whole electrolyte, that is Ba, but this is being the weak electrolyte, so some of the electrolyte is getting the dissociated and some of the electrolyte might not be getting dissociated. So what you can do, so in order to find out the degree dissociation, how much it get dissociated, we need to use this degree of dissociation term. So this term will tells you how much ions are getting dissociated. So for B plus and A minus ion, the total concentration is what? Concentration of electrolyte into degree of dissociation. So based upon this formula, you can get the actual concentration of B minus and B plus and A minus. So the concentration of undissociated molecules will be what? So alpha molecules get dissociated, so remaining will be what? 1 minus alpha, because we know that this alpha is what? Degree of dissociation, which is at most can have the value of unity. So we can subtract that value, so we will get the undissociated molecule. So if you multiply by using the concentration of electrolyte, you will get the concentration of undissociated molecule. So now just simply substitute that values in the equilibrium constant, so you will get finally the alpha square C upon 1 minus alpha. So this is the Ostwald law. You can come across this law in the 11-12 standard also. Okay, so this law will gives you the idea about the degree of dissociation of weak electrolyte and its concentration or the dilution. So it is known as what is Ostwald dilution law. So this is one famous law used in the solution chemistry. So it also states that whatever may be the value of concentration C, the degree of dissociation will varies in such a way that the value of dissociation constant, which is what? Alpha square C upon 1 minus alpha of a weak electrolyte, always remains constant at a given temperature. Okay, so this is the another statement. So it simply says that the degree of dissociation will remains constant at particular temperature. Okay, so temperature is a important parameter here. So in attempt to verify the above equation, the value for this alpha, we have already known that what? Lambda upon lambda m infinity, that the conductance ratio. So So we can simply substitute the value for alpha here, that is what, lambda m upon lambda m naught. So upon simplification you can finally get the value for equilibrium constant as alpha square c upon lambda m naught into lambda m naught minus lambda. So just simplification steps has been done here, nothing not tough mathematical thing. Just they have taken the ratios and some cancel out the common terms. So we know that this lambda is molar conductance and lambda m naught is the molar conductance at infinite dilution. Now this can be useful for calculating the equilibrium constant for the weak electrolyte. So upon measuring the conductance for the weak electrolyte by using Kohlrausch law, we can now use that for the finding out the equilibrium constant, and based upon the equilibrium constant, various parameters like Gibbs free energy, thermodynamic parameters like enthalpy, entropy change, all of these things can be obtained by using this dissociation constant. Okay, so this electrochemistry part will correlated with what, thermodynamic parts also. So we have seen that relation between equilibrium constant and Gibbs free energy at a standard condition, okay, standard state. So consider a specific example for related with this, that is the equilibrium constant. So at 298 Kelvin, the specific conductance of acetic acid, which is being what, weak electrolyte, is concentration is given as 0.05 molar, and the specific conductance is what, 3.678 into 10 raised to minus 2 Siemens per meter. Thus the molar ionic conductance at infinite dilution for H plus and acetate ions are they have given directly. So we need not to be like calculate for NaCl, HCl as such. They have given directly value for the H plus and